Much of what one studies in the beginning linear algebra course can be boiled down to the study of linear transformations. For example, we have already seen how elementary row operations can be viewed as applying linear transformations to both sides of the system. We now look at linear transformations more generally. Say V and W are vector spaces with scalars from the same field F. We say that a mapping T from V to W is a linear transformation if, for any two vectors x and y in V and any scalar alpha in F, the following two conditions hold. The first is applying T to x plus y is the same as taking the sum of Tx and Ty. Notice that this sum here is addition in the vector space V, whereas this sum here is addition in the vector space W. And the second is applying T to alpha times x is equal to alpha times T of x. And again, this scalar multiplication here is in the vector space V, whereas this scalar multiplication here is in the vector space W. Now, a couple of consequences of this definition are: 1. If you apply T to the zero vector in V, what you get is the zero vector in W. And you can see this by taking alpha to be 0 here. And the second one is, if you apply T to a linear combination of vectors in V, say a1x1 plus all the way to amxm, where a1 up to am are scalars, this is the same as the linear combination of the images. Now let's look at a couple of examples. Let's take a matrix A with entries in F for some field F and define the mapping T of x to be A times x. Then T is a linear transformation from Fn to Fm. And to see that this is a linear transformation, pick two vectors x, y from Fn and a scalar from F. Then T of x plus y is the same as A times x plus y, and by distributivity this is same as A times x plus A times y, and A times x is of course T of x, and A times y is T of y. Now let's check the second property. So T of alpha of x is the same as A times alpha of x, and by property of scalar multiplication this is the same as alpha times A times x, and this is simply alpha times A times x, which is alpha times T of x. Alright, so our T satisfies these two properties, and so T is a linear transformation. And let's look at another example. This time we're going to let T be a mapping that takes a quadratic polynomial in x with real coefficients to R2, and is given by this. So I'm going to show that T is a linear transformation. But before I do that, let's see what T of x squared plus 2x minus 1 is. So here, A is the coefficient of x squared, so that's 1. And B is going to be the coefficient of x, that's 2. And C is going to be the constant term, in this case is minus 1. So this is my A, this is my B, and this is my C. The first entry is A plus 3C, so this is 1 plus 3 times minus 1. And in the second entry, we just get A, which is 1. So this is going to be minus 2, 1. So how do you check that this is a linear transformation? Again, we have to check these two properties. And let me just do the first property. Let's take two different quadratics. Say a1x squared plus b1x plus c1, and a2x squared plus b2x plus c2. Then T of the sum of these two is the same as T of a1 plus a2 times x squared plus b1 plus b2 times x plus c1 plus c2. And then this is a1 plus a2 plus 3 times the constant term c1 plus c2. And here I just have a1 plus a2. Now I can rewrite this as a1 plus 3c1 and then plus a2 plus 3c2. And here in the second entry, I have A1 plus A2. And now I can break this up into two. The first one is A1 plus 3C1, A1. And the second one is A2 plus 3C2, A2. And the first term, of course, is T of V1, where V1 denotes the first quadratic. And the second is T of V2, where V2 denotes the second quadratic. So the first property is satisfied.